Today we're going to talk about kinematics in 2 dimensions. We're specifically going to be discussing projectile motion. This is our little mini unit that's going to enable us to both review and reinforce other things that we've been working on all year. So projectile is defined similar to how an object in free fall is defined. So let's talk about the similarities and differences. A freely falling object is an object that is dropped or thrown upwards or downwards. We'll just start with one that's going down. Let's assume it's starting at rest. And if it's dropped, it's going to increase speed on the way down. This should be somewhat familiar since we did it. And acceleration is equal to acceleration due to gravity. And the definition of a freely falling object is an object acted upon only by gravity. All right, great. So we know that this object only has gravity acting on it, which means it has a net force downward, which explains, right, why the acceleration is downward, because second law says, right, Newton's second law says that F and A have to point in the same direction. So that should make some sense. That also explains when you throw a ball upward, right, why it decreases speed, because you've got, right, if you're moving this way and your acceleration is down and your net force is down, these have to agree, you're going to have decreasing speed. So that, that should be somewhat familiar to you. Well, what's the difference between a projectile and a freely falling object? A projectile is given an initial speed horizontally, and then it falls while it's moving to the side. Now, why does it move to the side, right? So the work is done on it before it's a projectile. So back before this stage, something must have happened that gave it some initial speed. Once it left the launcher or the person's hand or whatever threw it, then gravity takes over. And if you look at the free body diagram for a projectile, it only has gravity acting on it. So what's the difference between, how do you define a projectile differently? Well, the only thing I would add to that is I would say, right, a projectile is all of that plus has an initial x velocity. Okay? So it's got some sort of push or thrust that gives it an x velocity. So, but the free body diagram doesn't change. It still looks like this. Therefore, there's still a net force down, which means there's still acceleration down. You'll notice there's no forces along the x-axis. Now on this one, when we were doing it, we're talking about the y-axis and we're moving on the y-axis only. But we could also talk about the x-axis having no forces, therefore acceleration on the x was 0. And because velocity on the x was 0, right, it was actually at rest. There was no motion on the x-axis, right? So we didn't have to worry about that for freely falling objects. However, for this object, we've got net force on the x is 0, right, from there. Therefore, we know acceleration on the x is 0, but there is a velocity to the right. Therefore, there's constant horizontal motion. So what does that look like? Well, if I were to draw the x component at every spot along this trajectory, it would be constant at every single point, the same value. And that's really hard for most people to understand, because when we look at a projectile, we feel like it's increasing speed or decreasing speed. But what you're thinking about when you're interpreting it that way is that you're thinking about the y component, because the y component does change, right? We've got vy, we have vy is 0 here when you launch horizontally. Then vy gets a little bigger. Then vy gets a little bigger. And then vy gets even bigger. You see how that's getting bigger and bigger? So that's the shape. And by the way, this path, right, this path of a projectile has a special name called a trajectory. So that's the word I'm going to be using. Yeah, so that's why those happen this way. So we've got this acceleration pointing down on the y, and since it's moving on the y, right, we can write this up. So net force on the y is down, therefore acceleration on the y is down, and vy is down, therefore, right, it's increasing speed vertically in this situation. And we saw that with the diagrams. So this is always true for all projectiles, even if the trajectory looks different. So let's look at a different trajectory. So let's say we had a ball, and instead of launching, it's called a horizontal launch. Let's say we launched it up at an angle. So what would happen next? Well, it would go up for a bit, and then it would kind of go down. So that's a typical trajectory. So we've got VO this way. Well, this can be broken into two parts. We can do Vx, and we're going to have Vy. And if we pick some other positions on here, we know Vx has to be constant. So all of those are Vx. Now look what happens to Vy. Here it goes up, here it turns around. So this is pretty typical of a trajectory. And you can do this for any shape, right? Any shape path, because all trajectories are parabolic for projectiles, right? So you can add that information in. That's kind of important too, right? They're parabolic. That's the shape of all of these, because there's only gravity acting on it, so there's a very predictable path that it's going to take. So again, you'll see here you've got net force on the y has to be down because this free body diagram here doesn't change. Therefore, acceleration on the y is down. Since it's moving up, when v is up and acceleration is down, that means decreasing speed. Right? We've been talking about motion diagrams all year. And again, on this half of the trajectory, right, this is Newton's second law, says that. And now for motion diagrams, we know when v is down and a is down, that means increasing velocity. So we've got like down the middle of this path, half of it's decreasing speed on the way up, and it's increasing speed on the way down. While all that's happening, right, meanwhile, Vx is this way, and acceleration on the x is equal to 0 because there's no net force on the x. Constant horizontal motion. These things are happening simultaneously. So don't let that confuse you. You have to know that this is happening the same time as this, but on the way up, and it's happening at the same time as this on the way back down. So you can't go with your gut. You're really going to have to make sure you're thinking about the physics here first. And since we're talking all about kinematics, right, we should talk a little bit about the graphs. And since we have two axes to talk about, we're going to talk about graphing on both axes. So we're going to have our x position and time, and y position and time. So we don't have any numbers here, but just let's think this through. If we know that, let's look at this one, right? Since we know that we're going up here, sorry, we're moving to the right the whole time, then we know that, and we know that it's constant speed on the x-axis, then we should be able to draw our graph shape because we know that it's moving at constant speed, and we know that constant speed on a position time graph is a straight line where the slope equals the speed. Okay, so that's because here, right, constant horizontal motion, right, because acceleration on the x is 0. For the y position versus time graph, again, we know the slope is going to be our vy, and here velocity points up, so it's positive, so we're going to have a positive slope. This part here, we're going to have a negative velocity, so we're going to have a negative slope. So we're decreasing speed, so the slope is decreasing, right? So on the way up, it's going to be positive and decreasing slope. And on the way down, it's going to be negative increasing. Oops, you can't see that, sorry. Negative increasing slope. So that looks like this. This is going to be at the max height, and then it's going to go back down again. So this we call the mid time. Okay. The whole time we're going to call the hang time. Okay, so here you can't tell where the mid time is, so you can just make it up. Here's your mid time. Here's the total time, which we call the hang time, the time in the air. Now you notice that this kind of looks like the trajectory, right? Now for this one, it would just be the second half. So we would start here and we would have just that half. Here we would start there, we'd have that half. Okay. Let's take a look at the other graphs we might make. What would a velocity versus time graph look like for each? And then we'll do acceleration time graphs. So let's do Vx in meters per second, and we'll do Vy in meters per second, and we'll do Ax in meters per second, and Ay in meters per second. All right, so let's go through these. So for Vx, since it's a constant speed and it's to the right, it's going to be positive. So we can just make a horizontal line, right? Slope of a VT graph is acceleration, and acceleration in this case equals 0. So we should have 0 slope. In this one, we know the slope of a VT graph is going to be acceleration, and acceleration is negative 9.8. So in this case, we're going to have a line that's like that, where we have positive values of velocity. This is on the way up. And here we have our negative values, so this is on the way down. Right, we have negative values of velocity. Here is where velocity is 0 just for that moment at maximum height, right? We're talking about like right here. At max height, velocity per second on the y is 0. Vx is never 0 because it's constant speed. So it doesn't stop completely, it just stops on the y before it comes back down. So we'll say Vy equals 0 at max height. So what's going on here? Well, we know that acceleration is equal to negative 9.8. So we would put a mark here. We'd be like, okay, here's negative 9.8. So that's a constant value for this kind of motion. And here it's just going to be 0, right? Acceleration is 0. So that's how we know that one. So these are, like, there are no other graphs. There's just different portions of this graph. So we're just kind of going back to basics here. Recall that the area of a velocity time graph is displacement. So in this case, it's going to be dy. Here, the area is also equal to displacement, but it'll be dx, right? The distance. And what are those values? Let's do that. So a typical diagram, if we were to do this, right, for a typical trajectory. So we would say here, if we're labeling, this is V initial, like either VO, right, Y. So you've got to have both X and Y while we're labeling. So this is 0, this is 0. This can never be 0. You may not have a projectile unless you have a launch speed. Always must be greater than 0. And we'll call this 0. Up here, this is where, again, V can never be 0. But Vx is some positive number. Vy is equal to 0. Time is greater than 0, obviously. This is at max. So this is Y position is going to be greater than 0. This is its maximum. X is going to be half of the total. We're going to call that range, right? So we've got all of that. Here at the end, right, we're moving down right here, this last point here. V, again, can never be 0 because we have not hit the ground yet. You have to have a Vx and a Vy. Vx here is equal to your V initial x, right? It's always going to be greater than 0. Vy here is going to be greater than 0. It's going, it's got a downward trajectory there. You've got a V, you've got two components, right? Vx and Vy. Your Y position is back at 0. Your X position, it's called range, right? Your total X distance that from here to here. There's a lot of symbols for this, but the name is called range. You can use delta X or delta dx, either one, okay? And this is going to be halfway. Then, what else? And then T is your friend. This is called your hang time, right before it hits the ground. One of the most common mistakes people make when they're doing that is that they is really with this, saying that when it hits the ground, either the beginning or the end velocity is 0. If you think that, then you don't really understand what a projectile is. So in the next video, I will teach you how to do problem solving, but these are all the conceptual and the graphical parts of this that you have to know. There's really the only new terminology you need to know are hang time, range, and trajectory, I believe. That's pretty much it. But you'll see how so much of this is kinematics that we've done before, a little bit of Newton's second law. We may work in a little bit of the law of conservation of energy, but that's about it.